Hi everyone, and welcome to How to Design a Stable High Frequency Amplifier. This is video number 6. And the objective for today is really to put this all together and to show you how to simplify stability analysis using a new probe called the WS probe. There's a workspace that goes along with this video. You can download it for free at the link below. I highly recommend trying it out. Alright, so far in this video series we've looked at many different techniques. We started with K-factor and studied loop gain. And there were lots of approaches, Oz-test, Middlebrook, Hurst, Tian. We looked at the return ratio, we looked at NDF, we derived them both internally across the transconductance terminals of the device, and we also looked at them externally at the device inputs and outputs. And finally, we looked at driving point admittance. Now, the circuit I've been showing is very simple, but let's face it, this is a lot of work to do to analyze this one circuit. And it's the current state of stability analysis. The benchmarks these days can be computed, it's possible to do, but it takes a lot of manual labor. The key to solving the problem lies with admittances. Throughout this video series, we kept coming back to admittance matrices as some kind of common theme. For example, the Hurst and Tian loop gains were explicit manipulations of an admittance matrix, and NDF was the determinant of an admittance matrix. The main issue we had was just deriving those admittances without perturbing the rest of the circuit or without doing multiple simulations like we had to do with the null injection. If you look in the design tools, there's one component that sticks out that might be promising. That's called the S probe, which you can put in your circuit and get bidirectional impedance, which is great. The big problem, and I think it's well known, is that it's not very accurate, especially when there's feedback involved. And that's, unfortunately, the place you need accuracy the most when you're analyzing stability. Let me illustrate this. I'm going to put the S probe in the middle of this very simple passive circuit, and it's so simple, in fact, that we can analyze it visually. At low frequencies, the feedback capacitor is open, inductors are shorts, and the probe sees a series RC combination on either side. At high frequencies, the inductors are open, and the probe sees a series of loop capacitors totaling 0.42 puff. So let's simulate this and look at the results. In the data display, I took the S probe results and decomposed them into R and C values, looking left and then looking right. And you can see at low frequencies, the S probe actually looks pretty good. We see series R's and C's like we're expecting. But when you look at high frequencies, this is where the feedback kicks in. It really breaks down. It gives a negative series resistance that should actually be 0. And at the same time gives negative capacitance. Well, that's not true. We know it should sum to about 0.42 puff. So this won't work for stability analysis. Well, as promised, here's the new WS probe in Pathwave ADS 2020. I'll make a copy of the circuit, and I will put the new WS probe in there and resimulate. And now let's compare the results between the two probes. You'll notice a big difference at high frequencies. The WS probe gives 0 resistance and series capacitance at high frequencies, and you'll see the values add exactly to 0.42 puff. This is the same number that we expected just by inspecting the circuit. So this probe provides bidirectional impedances in any circuit, even under the presence of feedback, in a manner which doesn't perturb the normal behavior of the circuit. Just a side note here, the WS probe is nicknamed the Winslow Probe after Tom Winslow. Tom is the engineer who developed it, and he's a distinguished fellow of technology at MACOM, and also a high-frequency circuit designer. And Tom struggled for years with some of these stability problems that we've been talking about today. And the nice thing is, along with the probe, he also provided equations that use the probe outputs to compute all the metrics that I've shown you in this video series. So this seemingly small tweak to an old probe unleashes tremendous amounts of power to circuit designers, and I'll illustrate that next. Now I'm going to go back to that amplifier feedback circuit that you should be very familiar with, and I will simply add 2 WS probes at the transistor and output nodes. And I'm also going to go down into the transistor model itself, and I'll add WS probes around the transconductance terminals internally. So going back up, I'll just run an S parameter simulation, and what I'm showing in the data display here is a lot of plots. It's actually every single stability metric that we've discussed in this entire video series on one set of plots. I've overlaid the process outputs from this one WS probe simulation. These are the red dashed lines on top of the results that we've meticulously derived earlier in the previous videos. Those are in blue. And you can see the results match perfectly. So you can run this one simple, easy simulation using WS probe and produce all of this and a lot more. So now we'll walk through it. Just for fun, I thought I'd put a scoreboard up to keep track of all of the simulations that it takes to reproduce this one WS probe result. So let's start on the top left with k-factor. Well, I computed this from the WS probe by reconstructing the Y matrix using this equation. And it's the same as terminating the two sides of the transistor input and computing k-factor. So that's one. All right, let's move to OS test. I computed this using an equation called WSP loop gain on the probe output data, and it matches our earlier result as well, you can see. But using the WS probe techniques, it's actually possible to emulate multiple different types of OS test configurations, which I did using these four simple equations here. And the configurations are forward OS test, we just showed that at the input node, and reverse OS test we can also do at the input node. That just changes the direction of the component. And we can also do forward and reverse OS tests at the output node. And additionally, the WS probe even allows you to change the terminating impedance to any value you want after the fact. So that's at least 4 separate OS test simulations inside just one of these WS probe simulations. Okay, next we'll move to Middlebrook. I computed that result from the WS probe just using the WSP loop gain equation, which technically replaces 2 simulations, because remember, there were multiple copies needed of the circuit for voltage and current injection. Now in this result, we did the injection on the inputs node, but you can also do it on different nodes. You can do it, for example, on the output side with the probes. So we'll add 2 more simulations to the tally. And we'll move to Hurst's loop gain. Remember, that was the one where we broke up the 2 blocks and characterized these individually. In this case, we use both WS probes to mathematically divide the circuit into those 2 blocks for analysis. And we do that using the WSP block calc function in ADS. Let's move to TN's true return ratio. The probe derives this, of course, for both input and output using the WSP loop gain function again with just a different option. Now, technically, the bench to derive the TN's true return ratio is the same as Middlebrook's, if you're clever about it, so I'm not going to add anything to the score for this one, just to be fair. Okay, now we'll look at internal return difference. The probes that I put inside the device can be used to derive internal return difference using a function which generates an arbitrary Y matrix from any combination of WS probes. So this is equivalent to that 4-port simulation earlier where we went inside the device, we added high impedance terminations to the intrinsic nodes and computed the S matrix. Just a side note here, for the WS probe simulation, of course, I still ran a sweep where I toggled the sources on and off to compute this. Okay, well, if we did it internally, we can also do it externally, just using the other probes. So we have external NDF, or return difference. It's the exact same procedure as the internal one, just using the external probes and generating a Y matrix with those probes instead of the internal ones. And that also matches the earlier result. And finally, we come to driving point admittance. That's derived directly from the probe output term, which is H0. And using the probes, we can apply this virtually to both the input and the output nodes of this circuit. So we replace 2 auxiliary generator simulations. Well, if you're keeping score, that's 14 separate simulations that we needed to just match one WS probe simulation. And the score would be a lot higher if the circuit was more complex, if there were more nodes. Okay, so now I think it's a good time to take a halftime break and talk about large signal cases. So everything we've discussed up until this point has been small signal, but large signal is a really important consideration as well if you're doing stability analysis. So I modified the working example to make it nonlinear and large signal, and to do that I first flattened the entire circuit blocks down and I replaced the input termination, which was just a resistor, with a one-tone source. Next, I went in and modified the transistor model. To make it nonlinear, I added diodes to the input and output, and these act as turn-on and knee voltages, which provides nonlinearity there. And because of the knee diode, I had to go back on the top level and add a DC bias to that as well. So now I will run a harmonic balance simulation on this new circuit, sweeping the power, and the results here show the nonlinear gain response versus power. So I think it's a good idea to analyze large signal stability at a power level which has gain compression. So let's do that at about Pn equals 10, and we'll just run one power point and then sweep the small signal around that. Okay, so we could do that for all the different cases, but I just want to take one into consideration here, and that's OS test. For a small signal, it was really easy. Remember, there was a built-in component. I just put it in the circuit. But for large signal, I actually had to go and build my own component to run this analysis. So this component has a separate one-tone source and some circulators which direct the signal around the loop. And I'll sweep this small signal source around the large signal operating point that comes from the other source. And to do that in harmonic balance, I have to go in and specify a small signal sweep. And I also took off the rest of the power sweep, so we're only going to analyze this at one power point. and then I ran the simulation. Now the simulation takes a few minutes for this because it has to linearize the circuit, but we'll just jump to the result. So to compute the loop gain now, I need to go into the harmonic balance mixing matrix because I have to make sure I specify the small signal tone for the voltages as opposed to the large signal tone. And then when I do that, I can take the voltage ratio across the OS test component for input and output and plot it here. Now think about what a hassle all of this was. This was a lot of work, and imagine repeating that process for every other benchmark that we did up until this point. This is pretty typical. Large signal stability test benches are often completely different than the small signal test benches, and the data processing is also different as well. Okay, well now let's take this same circuit and instead analyze it with WS probes. We'll use the same WS probes that we used last time, both outside the device and inside the device. To do that, I'm going to go click on the harmonic balance controller, and I will go to the small signal tab, check perform stability analysis. That activates the probes in the large signal simulation, and then I can just simulate it. So the simulation takes a few minutes, but once we have the result, we can just take the same small signal equations that we had before, that whole entire data display, and we can simply apply the large signal outputs to that as well. So the same equations and the same plots can be used for large signal and small signal simulations because the probe outputs are exactly the same. And that's not true at all for the individual test benches themselves. We need completely different equations to get the results. If you look at these results, you can see they're shifted a little bit. And what I'm really doing is comparing the large signal WS probe results to the small signal test bench results from earlier. So you can see how they shifted a little bit. I didn't even bother to run all these large signal test cases, for Middlebrook, Hearst, TN, NDF, driving point, because, well, it would have taken a lot of work to do that, to generate all those benches. But it's easy to do with the WS probes. So the final score here is 2 Winslow Probe simulations, one for small signal, another for large signal. These are equivalent to 28 separate analyses for large and small signal stability, plus all of the results processing. And these are just the ones that I showed in this video series. There's a lot more that you can do as well with these probes. And this is the power of using the WS probe to unify your stability analysis. To close, I wanted to go back to that tangled web of techniques that we started with. And what I hope you've seen is that with the WS probe, we can unravel this and turn this complex spider web into more of a toolbox for designers. I want to thank Tom Winslow at MACOM for collaborating with our team at Keysight to get this awesome capability out to the design community. And all that's left to do now in this video series is just to illustrate how to use the probe on some real practical circuit examples. I'll show that in the next video. Until then, download the workspace and subscribe to our channel for updates. Thanks for watching.